Okay, so an X-ray's coming in, it's shot at a piece of graphite, yeah, and we could, yeah, just assume it's an electron that's being hit. The X-ray is observed to have scattered at an angle of 15 degrees from the original path. So first we're asked to find the wavelength of the scattered electron, or X-ray, sorry, so the scattered photon, and then the energy of the ejected electron. So I'm just going to draw a little diagram first. So here I have my incoming photon. It hits an electron. It doesn't really tell me like east, west, north, or south, so I'm just going to kind of guess, and I'm going to put my scattered photon, it's going this way, and this has to be an angle of 15 degrees, and I don't know, say my electron goes off this way. I'm not told directions, so it's just a hypothetical direction to help me visualize what's going on. So this incoming photon has a wavelength of 1.28 times 10 to the negative 12 meters. The X-ray is observed to scatter 15 degrees. Okay, so that's everything that I know so far. So I'm being asked to find the wavelength of the scattered X-ray. So I'm being asked to find what this wavelength is. So basically, what we could do is we could find the change in wavelength. Okay? If we can find the change of wavelength, we know that change of wavelength is equivalent to wavelength final minus wavelength initial. So I'm going to relabel this as wavelength I, or 1, and this one is wavelength F, or final. Or you could say incident and scattered. So the formula that involves delta lambda is delta wavelength is equal to h over mc times by 1 minus cos of theta. So we don't have to rearrange anything, we can just put our information in. Again, make sure to use Planck's constant that has joules in it. Your m is your mass of your electron. Now, if you put this all in at once, use lots of brackets. I would do something like calculate this and press enter and then multiply by that. But if you use enough brackets, you don't need to do that. So change in wavelength, when you put that all in, you should get 8.26607 times 10 to the negative 14 meters. So then, if I know, if I know that I need to solve for wavelength final, I can just rearrange that little formula. So I know my wavelength final is equal to change in wavelength plus wavelength initial. So 8.266 times 10 to the negative 14 meters plus 1.28 times 10 to the negative 12 meters. So your final wavelength is 1.3626, etc., times 10 to the negative 12 meters. To sig digs, 1.36 times 10 to the negative 12 meters. So then if you think about it logically, that should be a larger wavelength than what you started with, which it is. But generally, like even if, especially since you look at our angle's not that much. So it didn't really get deflected or scattered very much. So the change in wavelength is pretty small, but it is there, okay? So just thinking about that logically. So then part B, we are asked to find the energy gained by the ejected electron. So we're looking for EK of my electron. So this is where I use my conservation of energy idea. Conservation of energy. So conservation of energy would say, okay, all of my incoming or incident photon energy is equal to my E scattered energy of the photon. I'll just write that below here to make it even more clear. Plus my EK of my electron. So the one that I'm looking for is this. This is my question. So I'm just going to rearrange to solve for that value. So if I keep that positive, I have my EK of my electron is equal to E incident minus E scattered. Now the energy of your photon we can use from our previous lesson, where it's hc over lambda, okay? So EK of my electron is equal to hc over lambda, and I'm going to specifically say wavelength I or 1 or initial, because they're going to be changed, right? Minus hc over wavelength, you can either put final or scattered or something like that. Now, you could write in all of your values at this point and plug it all in, or you could summarize one more step just so you have to put in less into your calculator. H and C are both the same in here, so we can factor them out so we don't have to type it in twice, but it would be the same if you did. So H times C, 1 over lambda I minus 1 over lambda M. Just to make it one less step. Now we're ready to put in our data. So 6.63 times 10 to the negative 34 times by 3 times 10 to the 8, all multiplied by 1 over 1.28 times 10 to the negative 12 minus 1 over, and what we found out from our previous answer, okay? 1.36 times 10 to the negative 12. Ooh. Squeak in there. So our energy of our electron should be 9.426 times 10 to the negative 15 joules. 9.43 times 10. Now, say hypothetically that a question asked you to put it into EV, then you could just convert to EV from there as well. Okay, good with this one? Questions?